Hi everyone, welcome back. This is lesson 6-7, investigating graphs of polynomial functions. And I think you'll be happy to know I think this lesson is a little bit easier than the last two that we did, so let's get going. The objectives for this lesson. At the end of this lesson, you'll be able to use properties of in behavior to analyze, describe, and graph polynomial functions. You'll also be able to identify and use maxima and minima of polynomial functions to solve problems. The vocabulary for today is endpoint, turning point, local maximum, and local minimum. All right. You may have seen this chart before, so let's talk a little bit about it. It says polynomial functions are classified by their degree. The graphs of polynomial functions are classified by the degree of the polynomial. Each graph, based on the degree, has a distinct shape and characteristics. So notice that a linear function is going to have a degree of 1. That means we're going to have x when the highest exponent is going to be 1. Quadratic equations, as we've seen before, our highest exponent will be 2. A cubic function, its highest exponent will be 3, 4, and 5. And so that's pretty simple to see. All right, in behavior is a description of the values of the function as x approaches infinity, which is written out typically as x approaches positive infinity or negative infinity, like this. The degree and leading coefficient of a polynomial function determines its in behavior. It is helpful when you are graphing a polynomial function to know about the in behavior of a function. All right, so look at this chart. You're going to see this chart quite a bit in this next lesson, and it'll be good for you to kind of get it memorized in your head. This top half is when the leading coefficient is greater than 0, okay? So if we had a function that said like 2x squared plus 3x plus 4, our leading coefficient is 2, and that is greater than 0. And so let's look at if we have an odd degree or an even degree. Okay, in this case, I have an even degree, but sometimes it's odd. It could have been 3x squared. Okay, if it's odd degree, our function is going to do this. It's going to and let's look at what, as x approaches the positive, as x gets positive, the whole function goes positive. As x goes negative, right here, the whole function you see is going to go negative. If we have an even degree, as the x approaches negative infinity, as it approaches this direction, notice that my function is getting more positive. It's got an arrow going up. And as x is approaching positive infinity, as it approaches this direction, notice that my function is also going up, all right? Now, let's look at it when the leading coefficient is less than 0. That would be like if it was negative 2x to the third power plus whatever. Okay, my leading coefficient is negative, so it's less than 0. So when that happens, let's look and see what happens. If we have an odd degree, which I do in this case, as x approaches negative infinity, that means as it's getting more this way, what happens to my graph? Well, it actually is getting more positive. And as x approaches negative infinity, my graph is getting more negative, all right, as it approaches negative infinity. And now if my function had an even degree, so let's say it was negative 4x to the fourth, then, and actually this one is x squared, as x approaches negative infinity, this direction, my function gets more and more negative, okay? It approaches negative infinity. But as x approaches positive infinity, this direction, notice that my function gets more and more negative, okay? So these behaviors are going to be really important in this lesson today. So I hope I'm going to show you this chart frequently. All right, so let's take a look at this example. It says, identify the leading coefficient, the degree, and the end behavior. So the first problem says negative x to the fourth. Well, I know this is the same as like a -1, okay, and that is less than 0, all right? So my function is going to be, we're going to look at these, and my degree is 4, which is even, okay? So we can see what's going to happen to my function, all right? The leading coefficient is -1, which is negative, and the degree is 4, which is even. So as x approaches negative infinity, right here, then our function is going to approach negative infinity. And as x approaches positive infinity, the whole function is going to approach negative infinity. So we can see that this one looks like that. All right, let's take a look at the next problem. This one says 2. So it says our leading coefficient is 2, and that's going to be positive, okay? And it says the next thing we need to look at is the highest degree is a 5. 5 is odd, so we're going to look at this picture right here. And actually, I covered up all the information on it by doing that. So we're going to look at this information on the odd side. All right, so we can see that as x approaches negative infinity, our whole function is going to be approaching negative infinity. And as x approaches positive infinity, the whole function approaches positive infinity. Okay, try one on your own. Take a look at this next problem and see if you can figure it out. You need to find the leading coefficient, the degree, and end behavior. All right, so here's your first one to try. Just take a look at that for a second. Okay, so let's see what you see. So first of all, and there's the second one, sorry. So first of all, we see that the leading coefficient is 2. All right, that is positive, so we're going to be looking up here. All right, next we see that the degree is 5, and 5 is odd, so that means we're going to look right here. So all the information we need is going to be here and here, okay? So it says as x approaches negative infinity, the function is going to approach negative infinity, and as x approaches positive infinity, our function is going to get more and more positive. All right, our second equation here, go ahead and look at that one for just a second. Okay, you should be able to see that the leading coefficient is -3, so that means we're going to use this side. All right, and our degree is 2, that's even, and so we're going to be looking at this function, so you can already tell what's going to happen. As x approaches negative infinity, the whole function approaches negative infinity, and as x approaches positive infinity, the whole function is going to approach negative infinity. All right, let's try this example. It says to identify whether the function graphed has an odd or even degree and a positive or negative leading coefficient. So the first thing I notice is that as x approaches negative, my function is getting more and more positive. And so I can see that that's what's happening in this one, and it's also happening in this one. Now I have to look at my ending. As x is approaching more and more positive infinity, my function is getting more and more negative. And so that one looks like this. So I can tell right away that my leading coefficient is going to be negative, less than 0, and it's going to be an odd degree. So let's just take a look. X is going to be an odd degree with a negative leading coefficient. Here's another one to try. All right, this time as x is getting more and more negative, my function is getting more positive. So I can see again that it's going to be this one or this one. And as x is approaching more and more infinity of the positive side, my function is getting more positive, so it would have to be this one. So that tells me my leading coefficient is positive, and I'm going to have an even degree. And there it is. It's even degree with a positive leading coefficient. All right, next. All right, take a look at this one on your own and see if you can identify this. I'll give you a little hint. You can take a look at that one. Okay, so you can see as my x is getting closer and closer to infinity, negative infinity, my function is getting more and more positive. So it could be that one or that one. And now as I go more and more positive, my function gets more and more negative. So I can see that its leading coefficient is negative, and it's going to be an odd degree. There it is, odd degree with a negative leading coefficient. Next, one more. Try it on your own. You may want to go ahead and write this down, this chart that we've been using, so you can have it in your notes. Here we go. As x gets more and more negative, my function gets more and more positive. All right, and as x gets more and more positive, my function gets more and more positive. Okay, it could have been that one, but in the end, it is this one. So I can see that I have a leading coefficient that's positive and an even degree. All right, even degree with a positive leading coefficient. I think you can start to see how the pattern works on that. All right, now that you've studied factoring, solving polynomial equations, and in behavior, you can graph a polynomial function. Here are the steps that you're going to take, and they look like a lot, but I don't think you'll find it too challenging. So the first thing we want to do is find our real zeros and y-intercept of the function. So fortunately, we don't have to worry about the imaginary numbers or numbers that have square roots on it. Next, we're going to plot our x and y intercepts. Then we're going to make a table for several x values that lie between the real zeros. Then we're going to plot the points from your table, determine the end behavior of the graph, and sketch the graph. So let's take this example. We're going to graph f of x equals x to the third plus 4x squared plus x minus 6. Now you can already kind of guess about what this is going to be looking like because we've been just doing that problem. So let's see what the first thing I want you to do is to identify the possible rational roots by using the rational root theorem. Now remember, the rational root theorem says to take this last constant, which is -6, and we're going to have to find all the factors of -6 over the factors of 1. So this is going to be really easy. We're going to have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So I think they're actually listed right there. All right. The next thing we want to do is test them. Now you can put this in your calculator and get a better idea if you have a long string of numbers here. For our purposes today, we're just going to test x equals -1. We should always test 1 and -1. All right, and so the way we're going to test it is by using our synthetic division. So here we get it set up, and okay, I did it really fast, sorry. Okay, so first bring down your 1. -1 times 1 is -1. Add these together to get 3. -1 times 3. Add these together to get 2. But notice in the end, I get a -4. That's not a 0. So that tells me that x plus 1 is not going to be a factor. So let's try +1 now. All right, and when we do that, and here it is really fast, and we see that we do get a 0 there. So we know that x minus 1 is going to be a factor. All right, so here we have x minus 1 is going to be a factor. And notice that this is going to be 1x squared plus 5x plus 6. Now when I look at this, I can go ahead and factor that out. Two numbers that multiply together to get 6, add together to get 5, are going to be 3 times 2 and 3 plus 2. So my last factor is going to be x plus 3 and x plus 2. So now I see that I have 3 roots. I have a root at 1, I have a root at -3, and I have a root at 2. Okay, so next thing that we want to do is write our equation out again in factored form, and there it is. And we see that our zeros, or our roots, are 1, -2, and -3. So I just want to sketch that out for us real quick so we can kind of get an idea of where that is. So I have a 1 here. I'm going to have a negative. Okay, there's -1. Here's -2. And here is -3. So I know that something's going to happen at these 3 different points. Okay? So the next thing I want to do is plot a few other points as guidelines. So the first one I'm going to do is I want to find what y is. When x is 0, what is y? So I want to find my y-intercept. So I'm going to fill in for 0 in here. And I can see 0 minus 1 is -1 times 2 times 3, because 0, 0, 0. So 3 times 2 is 6 times -1. So I know down here at -6, I'm going to have another point here. Now, I'm not really sure what's happening between 3 and 2. So what I want to do is go ahead and choose x. Here is -5/2, which is 2.5. So I want to go ahead and find out what's happening in between my 3 and 2 here. I also want to know what's happening in between my 2 and my 0, what's happening in this space here. So I'm going to go ahead and test for x equals -1. So what I need to do is fill in 2.5 and -1 for x and try and solve for those. So when I do that, I find out that when x is 2.5, y is 0.875. And when f is -1, y is -4. Okay, so at -1, I know that y is -4. That's somewhere down here. And notice when x is 2.5, my point is only right here. So I'm kind of starting to see a little bit of look of what is going to be happening on my graph here. So let's just turn the page and see a little more clearly. Okay, so here's my original. We saw just a minute ago. I'm going to kind of put a rough sketch in here again. I knew there was something here. I know there's something here at -1, at -2, and -3. I have points here and another point up here somewhere. So let's see if we can figure out the identifier in behavior. Okay, so I have a number greater than 1, so that's going to be on this top part. And the degree is odd, 3. So what I'm going to be doing, I'm going to start down here, but I'm going to end up this way. All right? So let's go ahead and plot that. We're going to graph it, and you can see it starts down here and goes up, and it pretty much is following exactly what we thought it would. Okay, so here's what we kind of had some idea that it would do something like this. Okay, so this is what you're going to be doing, and so I'd like you to try one on your own now. All right, you're going to graph this function. So turn off the video for a minute and give it a try. Okay, so the first thing you want to try is you're going to identify the possible rational roots by using the rational root theorem. Remember, we're going to take our 6, and this is a 1, so we just have to find what our choices could be, and again, it's 1, 2, 3, and 6. You could graph this in your calculator and see if any of them show up. We're going to test for the possible rational zeros. Again, we don't have to worry about the irrational and the imaginary ones. So let's first just test with -1 again, and it's going to go really fast. Here's our synthetic substitution or division. With -1, we end up with 8, so that's not very helpful for us. Let's try +1. And this time, when we do our synthetic division, we actually end up with a 0. So usually you should always try this one in -1. Hopefully you'll get it within one of those tries. So now that tells us that one of our x's is going to be x minus 1. All right, now notice here, let's see, that I have x squared minus 1x minus 6. So let's see if I can factor that out a little bit more. Two numbers that multiply together to get -6, add together to get -1. Well, that's easy. It's going to be -3 and 2. All right, so we're going to end up with x minus 1 times x minus 3 times x plus 2. All right, so next thing we want to do is go ahead and write the equation in factored form, which I just did for you. So it tells us that our zeros are at 1, -2, and 3. So you might want to go ahead and sketch out just a little bit to get an idea. I've got a 1, I've got a -2, which is right here, and a +3. So that would be here. So it looks like I have points at -2, +1, and +3. All right, next. We should plot some other points as guidelines. So let's pick something in between our points, something between our -2 and 1, and something between our 1 and 3. So, and always do your y-intercept also. So when x is 0, we fill 0 back in here. We find that our y-intercept is at 6. So that's going to be way up here at 6. 1, 2, 3, 4, 5. We'll put it way up there. Okay. And another choice might be -1 and 2. All right. So at f of x is f of -1 is 8. So that's way up there. And f of 2 is -4. So that's going to be way down here. So you can kind of get an idea of what our graph is going to look like by now. You can study the end behavior. Let's take a look at our cheat sheet here. Let's see if I put it on here. Yep. Okay, so notice that this was a positive and our, oh, sorry, that's a positive. And our leading degree is 3, which is odd. Okay, so we're going to be looking at something like that. And sure enough, here's what our graph would look like. Hope you got that. All right. Try another one on your own. Graph this function. Turn your video off, give it a try, and then come back. Okay, so you want to identify the possible rational roots by using the rational root theorem. Again, there's our choices that we should try. You want to test all the rational zeros until a 0 is identified. So this time they say go ahead and let's test x equals -2, just in the interest of time here. When we do 2 and do our synthetic division, we get 0 there. So we know that x plus 2 is going to be a factor. All right, and then that would leave us with 2x plus 3. All right, so the next thing we want to do is the equation is in factored form. Here it is. And our zeros are at 2 and 3 over 2. And how we got that one is we said -2x plus 3 equals 0. Subtract 3 from both sides. -2x equals -3 divided by -2x. Oops, divided by -2. X equals 3 over 2. So just in case you wanted to see how that happened. Okay. So now we have our roots, so we know where our zeros are going to be. We can plot a couple of other points as guidelines. Always do your y-intercept, okay? And so here it tells us our y-intercept is at 6. Plot a couple of other points in between. I hope that you were able to do this. Again, we want to look at our chart. We see that this is negative and our leading coefficient is even. And so there's the graph, but let's check it out. It's negative and our leading coefficient is even. So it's going to be this one. And sure enough, that's what our graph would look like. I hope that you were able to find that pretty easily. All right, a turning point is where a graph changes from increasing to decreasing or from decreasing to increasing. A turning point corresponds to a local maximum or minimum. So I'm just going to draw this out so you can see it a little bit better. If I have a graph that looks like this, I see that I have a turning point right here. All right, I go from increasing to decreasing. All right, here I have a turning point where I go from decreasing to increasing. All right, this is called a local maximum, and this would be called a local minimum. This would be a local maximum, and this would be a local minimum. All right, so those are the intervals where it's getting increasing, then decreasing, or when it's getting decreasing, then increasing. Okay, a polynomial function of degree n has at most n minus 1 turning point. So let me just look at that. Let's talk about this. Let's see that this particular cubic function has an x degree of 3. So it tells us that it has at most n minus 1, so that would mean that it has 2 turning points. Here's a turning point, and here's a turning point. Okay, and at most, in x-intercepts, that means we have 3, so it has, at the most, we can have 3 points. 1, 2, 3. All right, it says the function has n distinct roots. Let's take a look at this one, which is x to the 4. Notice I have 1, 2, 3, 4 distinct roots. Okay, then it has exactly n minus 1 turning points. So again, 1 turning point, 2 turning points, 3 turning points. Okay, and exactly n x-intercepts. And again, we have 1, 2, 3, 4 x-intercepts. You can use a graphing calculator to graph and estimate maximum and minimum values. And we're going to do that next, and it's really quite simple. So let's move on. All right, try this example. Let's look at this example. It says determine the maxima and minima with a calculator. So the first thing we want to do is get our calculator out and type in y equals and put that function in, or the equation in, and estimate the local maxima and minima. So step 1, we're going to look at the graph. The graph appears to have 1 local maxima and 1 local minima. All right? Something here and here. Step 2, find the maximum. So we're going to press the second and trace to access the calc menu. And once you get the calc menu, you're going to choose number 4, maximum. And when you press that, you should find that the maximum is approximately 21.784 whatever. So this is approximately, and it can be found at when x is negative 1.7. All right, so that's how to find the maximum. And then to find the minimum, we're going to go again to second trace, calc menu, and choose 3 where it says the minimum. And this time you should find that the minimum is at y equals negative 19.78, and that happens at approximately positive 1.7. All right, try this one on your own. Get your calculator out, give it a try, and then come back. All right, so when you put that in your calculator, you should have gotten a graph that looks something like that. The graph appears to have 1 local maxima and 1 local minima. All right, so step 2 is to find the maximum. So we're going to press second and trace and go to the calc menu and press 4 for the maximum. And so you should have found out that the maximum is at y equals negative 1.9, and that happens when x is negative 0.8. And then you should have gone ahead and found the minimum. Again, push second and trace, go to the calc menu, press 3, and to find the local minimum, it is approximately negative 4.0, and it can be found when x is 0.816. All right, here's another one for you to try on your own. Turn the video off and give it a try. Okay, when you did that, you should have graphed, and it appears to have 1 local maxima and 1 local minima, just the same. All right, so there appears to be no maximum. There's nothing really high up there. Okay, find the minimum. So we're going to just press second trace, and then we'll hit 3 minimum, and the local minimum is at y equals negative 6. And that is the end of our lesson for today. I hope you found that a little bit easier than the last 2 lessons. I hope you have a great day, and I will see you soon. Bye now.